catalyzed halogenation, or alpha halogenation, you can introduce a second halogen, but like, let me use red to edit this. Yeah, I'm gonna use red to edit this, and we're just gonna, no, it's not an nucleophile. So in this case, can we add a second halogen? No, right? We don't have a leaving group, but, or we don't have a proton to deprotonate. But if this was a CH2, you could add a second one. It's going to be slower than the first, so you're going to have, in the end, I mean, unless you let the reaction run for a really, really long time, and have a ton of excess bromine, which, don't spill that on your hands, by the way, it's terrifying. In my undergrad organic lab, a girl spilled like liquid bromine on her hands, and like, it went from brownish yellow to bright yellow, and all the like, you know, all the like, not cracks, but like crevices, creases, all the tiny little creases in your hand. Like if you look really close, it's like, oh, there's like a bunch of little ones kind of between all of your hair follicles. Those all, that's where the bright yellow collected, and then those all got bigger and became, well, cracks in her hand, and that was unpleasant. I mean, she kept her hand, she was fine eventually, but it was terrifying as an undergrad organic student, and I'm pretty sure our professor was a bit concerned as well. So, yeah, careful with liquid bromine. That stuff is scary looking. And also, don't spill it on your hands over a sink too, because I mean, the worst part of that is that it got on our hands, but a side effect, liquid bromine definitely went down the sink, and I don't think Bolivar Water Treatment Center was prepared for that. I don't know what happened. But, so you can stop, even if you've got CH2 here, this is, the second edition of that is slow enough that you can stop at a single substitution, and you're gonna have to try and like put a bunch in and wait a really long time to actually get your two substitutions for acid catalyzed halogenation. So that's for acid. If you're doing this in acid, then you can substitute it just once, and you can stop it from substituting again, or you can wait like forever for the second one to go. Because the electronegative alpha halogen decreases the basicity. So this decreases, once you've got one of these guys, then now there's more electronegativity, like there's an electron, there's some electron density around this carbon and around that carbon, right? So this is slightly less basic because it's just got some stuff next to it. Not a huge deal, but with acid, you can just do one if you want. You can stop it with base. Each time you put a bromine on there or a halogen on there, the next one goes faster. So if you, well, okay, generally not a useful synthetic reaction. There's any electronegative? I don't know, that seems fine. I guess a useful synthetic reaction, meaning most of the time we do carbon-carbon coupling, and, or I don't know, most of the time you want a bromine on something so you can change that into something else, right? And I guess they're saying it's not overly useful to have two bromines on the same carbon at the same time, because if you, the next time, like when you go to turn that into something, you can't just turn one of them into something, you're gonna turn them both into something. But like, people in my lab have definitely done this, and they wanted the dye substitution, so they can take their generally and note that there's an exception. Let's see. All right. We're gonna do this, maybe the next one, and then we're gonna switch over. Now we're gonna do this. So most reactive to least reactive when treated with a nucleophile. So this is not the alpha halogenation. This is a question I took from like earlier in the slides. But we're trying to figure out what is most reactive and what is least reactive when treated with a nucleophile. That means that the carbonyl carbon is our electrophile in each of these. And, well, we're looking at a couple different things, right? One, we're looking at which one has, which ones are more electropositive. I don't know if that's a word, but are less electronegative. Which ones are better electrophiles? Yeah, which ones are better electrophiles? Which ones have slightly more positive charge characteristic? But we're also looking at something else, because what else is a factor on here? With this guy. Yeah, these butyl guys, those get all sorts of in the way for all things. So that one is going to be the least reactive, just because, I don't know, I mean, I'm pretty sure you could get that to react. I don't think that's going to completely stop it, but it's not going to be easy. It's going to be slow. All right, so which one of these three, which carbon has the most positive charge characteristic, or the most positive-ish charge there? Or the least electron density around it? C, right? Because, I mean, well, if we know that double bonds are usually stabilized by more substituents, not just hydrogens, then we know, okay, the hydrogens kind of go, they don't really help with having some electron density around this. So that's gonna have the least amount. That guy is gonna keep stealing all of that. That's gonna be the most reactive, right? Let's see. After that, okay, what is the difference between these guys? Or what is something you might be able to do, draw, structure-wise, with one of these that you can't with the other? Something you might be able to draw structure-wise, you know, in a resonancy fashion.
Like the keto-enol?
So, oh, well, yeah, okay. I mean, for either of these, we can deprotonate on this side only, and for this we can deprotonate on both sides. But this is a nucleophile, so we're trying to do nucleophilic substitution. So you can deprotonate the alpha carbon, but, and if we start doing resonance, it might start looking like we're trying to deprotonate an alpha carbon. But this guy can do resonance, right? Even though this guy is sometimes drawn with a ring, and we just are like, who cares about that? Really, it's best practice to always draw these, because then you don't miss things like, oh, this is an sp2 carbon right next to an sp2 carbon. Those are alternating double bonds. Even if these guys are aromatic, you can't really, like, they're extra super stable in that you're not going to break one of the aromatic double bonds, but they're alternating double bonds. You can totally resonate that. So B is going to be more reactive because, well, your resonance structure is negative charge up here, positive charge up here, down here, and this, and that's all. Here, you can move that positive charge all around, right? The bunch of resonance. Does that make sense? It's kind of a thing we haven't messed with yet, because once you start moving these guys, then you're, well, we just haven't done that, but you can go in circles with those, which is fun. Which will not produce an aldehyde or a ketone? That is a terrible question for right now. What? You haven't learned this. That's next chapter. Have you even learned about Dibol? Or Dibach? I'm pretty sure that's just Dibol. Have you guys heard of that? Okay, yeah, no. This is a terrible question. What on earth? Okay, the answer's 2, I guess. they threw other things up there so that you would get confused on, I don't know what this makes, and not realize, oh, we already learned PCC with OH and it doesn't turn into an aldehyde or a ketone, but I don't like that, that's dumb. Cool, let's talk about the thing they just tried to quiz us over. Carboxylic acids. All right. So, structure of carboxylic acids. They look like this, which has, well, some fun resonance. You can condense them by writing them COOH. If you write CO2H to condense that, I'm gonna make this face because I don't like it. And you're not technically wrong. Who would do that? A monster, that too. So don't be a monster. Aliphatic carboxylic acids, they're this carbon, and then connected to that you've got a carbon and some stuff, carbon chains. Aromatic, you're going to have a benzene or an aromatic ring directly next to this, which, if you remember from like 4.5 seconds ago, when we have, yeah, I'm taking it back. We're never allowed to draw this ever again. Yep, I took it back. Sorry. I thought maybe we would be okay, but it's not okay. Because resonance. So an aromatic carboxylic acid looks like this, and well, these are alternating double bonds, right? We've got double bond, nothing, double bond, nothing, double bond, or I guess nothing, single bond, double bond. So all of these carbons are sp2, right? So everything, all of that is planar. All of these guys are sp2 and in the same plane, so we can do resonance all over the place. And actually, these guys have lone pairs, right? And lone pairs don't have to exist in an sp3 orbital. In fact, because this is right next to here, no wait, no, these guys are in sp2 orbitals, right? Because we're already using the p orbital that comes out of the board to make this double bond. Yeah? We're good? Okay. But over here, that and this, those are sp2, and we're not using the orbital that comes out of the board, which means one of these guys is in a p orbital, and we can do resonance throughout this whole thing. All of it. All of it can do resonance. It's wild. Yeah? You don't have to know, like, this is just my way of explaining why we can do resonance with all of this stuff. You don't have to, like, I'm not gonna, like, point to lone pairs and be like, what kind of orbital is this in? Because, I don't know. You already learned Vesper, so I don't want you to identify things. I just want you to be able to use that stuff to do chemistry, yeah? Okay, so if you have a carboxylic acid, you drop the E and add oic acid. So methane, methanoic acid, ethane, ethanoic acid, 3-methylbutane, 3-methylbutanoic acid. 3-methylbutane is wrongly named, right? Because if I actually just had 3-methylbutane, it would be 1-methylbutane, because there'd be no reason to start numbering over here. But whatever. but 3-methylbutanoic acid because we start numbering from the carbon on the carboxylic acid. Yes? Let's see. If the compound contains a double or triple bond, then you just put an N or ein instead of an an right before it. So, why do they have? Oh, okay. Sorry, I was looking at the wrong thing. Propenoic acid or propenoic acid, butanoic acid. Why didn't they put a triple bond so we could have an inoic acid? I don't know. Carboxylic groups takes precedence over most other functional groups. There's a couple that it doesn't. We've got a flowchart later because you don't have to know. There's nothing that takes precedence over it now, because we haven't learned any of that. Once we get to the next chapter of carboxylic acid derivatives, then there's a nice little flowchart of reactivity and stuff like that. But basically, most of the time, if you have a carboxylic acid, that's the one you should probably start numbering with. Dicarboxylic acid is dioic acid, and, well, I mean, a carboxylic acid takes up, just the functional group takes up 2 of the bonds on an sp2 hybridized carbon, so there's only 1 left, which means if you've got 2 carboxylic acids, in order to have the main chain contain both of them, you have to start and end with it, right? There's nowhere else in the middle for it to go, unless you're just not including the actual carbonyl carbon in the chain. So include both of these carboxylic acid carbons in the chain, and even if you've got, oh wait, I need more carbons to do substituents. Even if you've got this, these take precedence, so name this as an ethane dioic acid and this is a propane dioic acid. Propane dioic acid or malonic acid, and count those carbons and make it an alkyl chain. Yeah? Okay. If the carboxyl group is bonded to a ring, then, well, we still start numbering with 1, both because it's a ring and we start wherever we want, and also because these are always terminal. So we start from there and we count in whichever direction gives us the lowest numbers, and instead of oic acid, you just, keep the E at the end and just add carboxylic acid to the end of it. No space between the, whole last name of a thing and carboxylic. Just smash it on there. No space needed. We only need a space between carboxylic and acid because we're chemists and we want to win at Scrabble. I don't know how else to describe that, and this is how we do it. Let's see. Numbers are used to show the location of substituents relative to the carboxyl group. That is a weird 1,2-benzene dicarboxylic acid. Yeah, okay. So I guess, when we've got benzoic acid, when we've got a benzene ring, basically none of these none of the participants in the ring can be the carboxylic acid, so it's just, we know it's stuck to one of them, so we just put the numbers that they're on. We don't have to number if it's 1, but you can number the other things with relation to it, or number 1, 2, benzene dicarboxylic acid, 1, 4. Doesn't super matter. I'm not going to make you name all of these. Okay. For common names, oh hey, this tells us, I never remembered delta's next. So this is where the alpha carbon or alpha hydrogen nomenclature comes from what we were talking about. That's why it's the alpha carbon. It's the carbonyl and then alpha, beta, gamma, delta. So with a carboxylic acid group, you can only count in one way. So there's only one alpha, beta, gamma, and delta carbon, and it's not ambiguous like the others. Let's see. That, just a CH3 and a carbonyl is a aceto group, like acetone. So that's the thing. Anyway. So, physical properties of carboxylic acids, far more interesting than name, right? We have until 9:40. Okay. Physical properties of carboxylic acids. These guys are, well, this whole part of it is planar, right? We've got a whole lot of electron density on the carbonyls. So we've got red for all of that electron density, and then we've got some electron density down there, but we've got a hydrogen there. And these guys, much like alcohols, can do some hydrogen bonding. But, I don't know, I'll draw my GQs. These guys are going to have, in liquid and solid states, they can do that. So, based on the picture here, what do you guys think is going to have the higher boiling point? An alcohol or a carboxylic acid, assuming that they both have about the same molecular mass?
Carboxylic?
Carboxylic, right? Because, well, an alcohol that, and then you can have another alcohol. 1, 2, 3, 4. 2, wait. Oh, yeah. 1, 2, 3, 4. Yeah, and you can have that, right? You can have a nice little hydrogen bond holding those together, but this has that amount of electron density, right? Like, it's not 2 lone pairs and like on a trigonoplanar, it's 2 lone pairs on a tetrahedral, right? So it's kind of a smaller section and not, all the way out there. Whereas, well, I guess you don't really have to draw, but whatever. This is, let's see, I can do things. Okay. To make those guys stop hanging out together and like boil off one of them, you've got 2 hydrogen bonds to break, right? So they're holding on to each other a whole lot stronger. Hydrogen bonding, I don't know if you guys, when you first learned about this, you probably learned that there's, in like DNA base pairing, that's kind of how DNA base pairs stick together. So it's not just with carboxylic acids like this, but it's with hydrogen bonding, and there are carboxylic acids and adjacent things involved in that. I think one of the base pairs, if you get into biochemistry, when you start if you look at how stable, like how well 2 DNA strands, or I guess even RNA strands, will stick together, you start looking at the proportion of CG and AT. Are those the? Yeah, that's not RNA, that's DNA, right? CGAT? Okay. One of those you replaced for RNA. Clearly, I would totally be qualified to teach biochem. I don't remember which one, but one of these has 2 hydrogen bonds holding it together, one of these like pairs, and one of these has 3 hydrogen bonds holding it together. So basically, that's, if eventually you start looking into like how stable are they, or like designing your own primers, that's something you have to look at, how many CG versus AT, like the percentage you have, because if you have too much of whichever one only has 2 hydrogen bonds holding it together, it's not gonna bind as well, and it might, get off or something. Okay, yeah. Higher boiling points than others, even alcohols, partly because they're polar. I mean, they're way more polar than alcohols, right? Because well, they've got the carbonyl polarity, which is like a huge section of red there of lone pairs. And then they've also got the hydrogen bonding of alcohols, so they beat both of them. They're more soluble in water than alcohols, ethers, aldehydes, and ketones of comparable molecular weight because, well, they can hydrogen bond. Like, water can hydrogen bond the crap out of it, so it's just surrounds it in a nice warm hydrogen bond hug, and it's much better at dissolving. I don't want to look at a boiling point chart. Who cares? Okay. Physical properties of carboxylic acids. The solubility in water decreases as molecular weight increases. So yes, this is hella polar and wants to do all of the hydrogen bonding with water, but you stick enough carbons on there, and that's just not enough to actually make it soluble in water, right? If you want to put this many carbons on there, and you still want it to be soluble in water, you're going to have to do, well, something else to it. Probably, I mean, in terms of organic chemistry,